Hello, my name is Michaela Mönikes, and I'm happy to guide you through the interesting content of this session within the world of electrification and automation. Our next speaker is my dear colleague Oliver Schrödel, and he will present a behind the scenes. Oliver will take us to the largest onshore fish farm in Norway and its self-optimized grid. Please post your questions at any time during Oliver's presentation so we can answer them live at the end of his presentation, where we have a dedicated Q&A session. I will then take your questions and address them to Oliver. Please make intensive use of this possibility to directly address the expert. We are here for you. And yes, we will record this session. Oliver, I know that you would like to focus on the self-optimized grid, and I guess that the auditorium is curious to learn about the SICAM application in Norway. The stage is yours.
Hello and welcome to our conference session Behind the Scenes, Self-Optimizing Grid and the largest onshore fish farm in Norway. My name is Oliver Schrödel. I'm Senior Key Expert for Distribution, Automation and System and Product Lifecycle Manager of the SICAM application Self-Optimizing Grid. Let's start with the agenda for the session. Chapter 1, Behind the Scenes, the Future of Energy System. Chapter 2, A New Approach, the largest onshore fish farm in Norway. Chapter 3, Self-Optimizing Grid, Intelligent Electrification and Automation. And finally, Summary. Chapter 1, Behind the Scenes, Self-Optimizing Grid to the largest onshore fish farm in Norway. I like to give an overview on the use case. So how this specific appliance on an onshore fish farm has similar needs like our traditional distribution system operator, and how this will collaborate with the future of energy system. But first, to the final output of our onshore fish farm. It is perfectly grown-up salmon, raised in clear and clean water from the Norwegian coast. This is not enough for the customer. He likes to raise the salmon in clear and clean water with the best level of energy efficiency, lowest carbon dioxide footprint, and lowest ecological impact. This leads us to the future of the energy system, which is subjected to considerable changes. The distribution grid must deal with many new topics, embrace electrification, tackle efficiency, and connect infrastructure, where decentralized power supply and volatile infeed and new load scenarios like increased requirements from electromobility play a decisive role. And engage IoT, where grid edge devices of distribution automation helps to maintain the grid. How fit the drivers for the future of the energy system together with a new system of a fish farm? What are the similarities of the future energy system in a new onshore fish farm? I will share some topics. Optimized energy consumption. Combining clean and fresh seawater with reuse means energy consumption for pumping and heating water is minimized. The energy plant has a very high performance in relation of the energy used. That contributes to a competitive operating costs, even compared with farming in the sea. And treating wastewater and reusing sludge will also help to minimize the environmental footprint, and is one of the contributors of a circular economy. Waste from the production are collected and will be used as raw material for biogas production. An increasingly complex and interconnected electricity system demands a more sophisticated technological infrastructure. Bringing the challenges of the energy system of the future in an overall picture, the study of a cooperation with the European Distribution System Operators, EDISU, showing the way forward. In the study, recommendation on the role of the DSO and the European Unit's recovery plan and acceleration of the Green Deal agenda. With the development of smart grids, new data-focused business models, and overall digitalization defines also a technological infrastructure which can deal with these challenges, like the electric vehicle, smart charging, and grid integration, balancing supply and demand, and better grid maintenance. We are online monitoring via cloud, can predict, prevent outages, or support the fault location. This use case is already connected to the demand on our onshore fish farm. But the most important this session today is the Selfhealing network. Selfhealing network supports smart grids to identify faults, isolate the affected part of the grid, and where possible, reconnect and re-energize the system as fast as possible. The self-healing application is the core of the application and distribution automation arena, and it's integrated in our SICAM application of self-optimizing grid. And it is exactly the same application we present now in our session on the largest onshore fish farm. Chapter 2, a new approach for the largest onshore fish farm in Norway. And we deliver the resilient power system to safeguard substantial onshore aquaculture in Norway. The project is currently under development, and here is the plan in its full extent. It's located on a kind of island on Norway's coast. The project started with Siemens medium voltage team for distribution switchboards, but ended as a full electrification and automation delivery, including offerings of distribution solution and digital grid. I would categorize it as an industrial project. Instead of a power grid for a city, we have fish plant that is very vulnerable for fault in the electrical power supply. 5 million liters of crystal clear seawaters flooded from the deeps of 95 meters into each of the tanks during startup. Taken from the open sea, this inflow has a temperature of 8 degrees Celsius. Fish health is imperative to a substantial aquaculture operation, and with the tanks containing 36,000 tons of fish, uninterrupted high-quality power supply is key to customer requirement. Moving the operation on onshore is desirable, but challenging due to the large amount of energy required using for pumping the seawater into the fish tanks. Approximately 39 megawatts is needed to exchange the water every minute. This energy demand is not only for pumping fresh seawaters into the flow-through and new flow-through technology with reuse of the seawater about 65% and replaced every 4 hours in a tank. First setup. The system is designed in such a way that it will be easily expand and build next phases of the fish farm. In the first stage, our system is working in a radial distribution grid, but we have the possibility to reclose switchgear closest where the fault occurred. In the end of the phase, the project and the customer will create a distribution ring inside the plant that enable to energize fast in all paths except the fault location. Chapter 3. Self-optimizing grid, intelligent electrification and automation. Let's have a closer view on the self-optimizing grid application itself and how the system is implemented. Intelligent electrification and automation and the SICAM application of self-optimizing grid. Our application is based on our standard product portfolio and it extend our automation system. This screen shows the human-machine interface of our SICAM application self-optimizing grid, which visualizes the state and enables the operator also to take over control of the self-healing system. The system is working in a semi-centralized architecture where all relevant decisions are made on a regional controller. The main intention of a semi-decentralized approach is to create clusters in the network meaning that small areas can be deployed closed-loop automation. The data from the field is automatically processed and commands are sent without any human intervention. SciChem self-healing and most relevant use cases. The SciChem application of self-optimized grid is comprised of the most relevant application for semi-centralized solution. These applications are currently monitor the grid and remotely control the station to ensure high reliability of supply and improved system performance in a closed-loop implementation. The most relevant use cases are already integrated, which I mentioned during the challenges of the European distribution system operators beginning of the session. For self-healing, we integrate the functionality for self-healing and for automatic source transfer. For the functionality of balancing the load and the demand, load management and overload reduction. And in addition, for fluctuating loads created by electric vehicles, there's a functionality available of the area voltage control. Self-healing use cases are applications that restore your distribution grid in seconds. I like to present now how the self-healing is working in a simplified way and how we improve the performance for distribution grids in closed-loop automation switching solution. In the middle, there is a layout of a typical distribution grid. The distribution grid consists, in our sample, of cable and ringman units with integrated remote terminal units, short circuit indicators. On the top, the grid is monitored with our regional controller, including our SciChem application of self-optimizing grid. In case of a cable fault on the line, the circuit breaker on the in-feed substation trips and the consumer on the line are de-energized. All information from the field level gets simultaneously reported via e.g. ISE 6150 to the regional controller. The regional controller calculates the fault location, starts immediately the isolation of the faulty cable segment. And the regional controller energizes the grid by closing the in-feed, circuit breaker and the load breaker at the normally open point. The self-healing will handle these events autonomously and just in a few seconds. The sequence can be even faster using circuit breakers instead of load breakers. This application supports reduction of outage times. Here especially saves the lives of the fish at the farm. In general, it improves the distribution grid reliability indexes. It reduces the fault location costs, and the solution is open and can flexibly adapted to existing secondary substation or to extend the grid layout. It reduces extremely the workload for the operator in the event of several simultaneously faults. Semi-centralized approach integrates all field-level devices. Let's have a closer view to the system architecture of our self-optimizing grid and how the application is integrated in our secondary systems. As mentioned, our application is based on standard substation automation products. Our regional controller of the self-optimizing grid is hosted in an automation system of SciChem PAS, and the human-machine interface is located at SciChem SEC. You can easily find it at the blue rectangle in the middle. The regional controller can place direct in the primary substation or can supervise multiple primary substations. Directly connected to the regional controller, the intelligent field devices in the substation like protection relays and transformer controllers. In the rectangular of the secondary equipment on the bottom, you find all relevant equipment for handling overhead lines, reclosers with recloser controller, cable grids with ringman units, and remote terminal units. Also voltage regulators on the field level like RONs or pole-mounted AVRs can be integrated. Let's have a closer look what is really implemented in our plant, what is the reduced setup for the largest onshore fish farm in Norway. The dotted line shows the secondary architecture and which is used in our project. The plant is energized by a cable grid and uses mainly self-healing application. So you find the architecture based on in-feed substation with protection relays of SIPROTEC5 and ringman units with remote terminal units, SICAM A8000 and short circuit indicators of SICAM FCM. And that leads us to the final setup of the largest onshore fish farm in Norway. The centerpiece is still the regional controller, which is connected to all SIPROTEC5 relays and SICAM A8000 devices via the protocol of ISE 61850. Finally, I like to present the full technical principles of the secondary system, with all details, but still following the already known setup. On the top middle, you find two SICAM components, the regional controller, the PAS, where the SOG, the self-optimizing grid, is located, the SCC, where the HMI of our application is located. Below, you find the communication ring in orange and different substations with the communication implemented in fiber optics rings using ISE 61850. Protocol has especially feature of redundancy implemented. The secondary equipment and the field level, you will find different substations, each equipped with SIPROTEC5 relays and SICAM A8000 remote terminal units. All this communication is using the ISE 61850 protocol with a redundancy feature. As you may see, the secondary system already implements a high level of availability and supports the application of self-optimizing grid. Standardized grid topology and ringman unit design. Not only the secondary system has a high level of standardization, even more standard design is implemented in the defined ringman units for the plant. Following ringman units are used for the project. An in-feed station with 5 ring cable feeders with protection relay and remote terminal unit. Substations where you find 5 and 3 ring cable feeders with protection relay and remote terminal units. And distribution station with 2 ring cable feeders, short circuit indicators, remote terminal units. The single line showing, in this case, on the left side, 2 similar distribution stations, which are directly connected via a cable equipped with load breakers. Same is true for the world of the distribution grid operators. This layout is the most standard design of a medium voltage switchgear in distribution grids. Let's have a closer look to this view of the typical standardized station, 2 ring cable feeders with short circuit indicator and remote terminal units. The switchgear is a Siemens 80JH ringman units, which includes following additional components to be monitored and controlled. A SICAM A8000 as remote terminal unit, a SICAM FCM per cable bay as feeder condition monitor, a motor control unit for the built-in motor drive, a UPS, an uninterruptible power supply unit and battery, and low power CTs, so current measurement sensors, and low power VTs, voltage measurement sensors. And in futures, both of these CTs and VT sensors are integrated in an option of the C bushing. All substations of the project have a similar approach and includes a high level of integration of electrification and automation. Let's follow up with a summary. During the project, the customer is very happy with the performance of Siemens and the results of the SICAM application of self-optimizing grid based on SICAM PAS and SICAM SCC. It is a very good solution and it can be installed on industrial use as well on distribution grids. In these edge times, there is more need for this type of solution which acts regional. The application approach was based on the design of a self-optimizing grid solution in close collaboration with the Norwegian customer, the on-site Siemens team and the Siemens experts in headquarters. But also for us internally, it's a holistic approach of intelligent electrification and automation, where we bring the best Siemens together in one project of digital industry and Siemens smart infrastructure. addressing the customer key challenge in providing confidence in power system design. Our smart infrascope of electrification and automation contains ATGA switchgears, SIPROTEC5 relays, SICAM A8000 RTUs, SICAM PS and SICAM SCC, and the SICAM application of self-optimizing grid. With an option to implement cloud-based system monitoring and services through MindSphere, we're all enabling the possibility towards our topic from begin, better grid maintenance. Finally, I'd like to show some pictures of the excellent states of our behind-the-scenes self-optimizing grid of the large onshore fish farm session. First, the real layout of our first stage on the onshore fish farm in a beautiful Norwegian landscape. The customer is mentioning that he's planning to build more of these fish farms, planning to build fish farms on land on other parts of the world with the aid of the technology. In addition to the value potential offered by building similar installations elsewhere, this will allow the customer to be a beacon for sustainable development of global seafood production. The next pictures show a typical substation on site, a future ringmain unit for ringmain cable feeders equipped with SIPROTEC5 relays. And the last picture shows the Siemens project team with the project manager in front. The regional controller is running on the SICAM application of self-optimizing grid on the screen in the middle. The project team seems really to be happy, and I'd like to thank the team in Norway for this great passion for this extraordinarily highlight behind the scenes self-optimizing grid in the largest onshore fish farm in Norway.
Thank you, Oliver. That has been interesting insights into this Norwegian fish production, and I'm happy to learn that they want to breed fish on land, because I know that's better for the environment, and that we take care of the fish by providing this self-optimized grid that helps a stable supply for everything running there. And your presentation had definitely been of interest to our auditorium, because I see questions in my row here. So the first question is coming from PT, and PT wants to know, what are physical limitations to the system, such as the maximum distance in between SICAM A8000 or the amount of SICAM A8000, and are there more limitations? I have no clue.
Yeah, correct. Well, that is a good question, honestly. The distance between the SICAM A8000 doesn't matter, honestly, because we're using communication protocols like IEC 61850 or 104 protocol. And so long we have a certain infrastructure like here with fiber optics, distance is not a problem at all, honestly. That is so good on the one side. On the other side, I explained a little bit that we have the option to extend our system, but normally we're looking about a certain region. So 1 substation, 2 substations, 3 substations. To have this kind of regional approach and kind of regional clusters where we have an integrated solution of self-healing, voltage regulation, and so on. So that is not made for an overall, like in a control center. So we are somehow between control center and the field level and adapting a certain region. So that is the topic, what we are focusing on. And that is not a limitation. So that is a definition which we take.
Okay, thank you. Thanks. And what you've seen in the meantime, while Oliver was so very well explaining or answering the question, that was the view into the exhibition area. You can visit it at all times. And why did we show this up to you? There is this little red button. Here you can meet the expert. And Oliver is one of the experts that will be in the chat area after his presentation. Give him some time. He needs to answer some more questions here with me. I have at least 2 more in the line, I think. And he needs to go there, kind of, at least go to another PC. But then he'll be there and answer questions or chat there or talk to you there in the meeting room. And we take one more question. The next one is, Are all actuators controlled via IEC 61850 related protocols?
In this project, yes. In this project, we have this kind of redundancy ring, but nevertheless, in a distribution grid for DSO, it's different, honestly, because he has different protocols like 104 protocol, GNPO3 protocol, IEC 61850. We can also mix these protocols from the different field levels and connect it to the CyclePS. Most relevant is that we have a protocol which is known to which is known to the electrotechnical domain. So that is something which I like to mention. So, but the rest, if we have these kind of protocols, we are easy to integrate different protocols, different infrastructures.
Okay, thanks. That kind of already probably answered another question from the round. We take one last question, and that is, what kind of communication is needed to keep this application working? So we already mentioned communication.
Exactly. So the topic is, so we need standard protocols, which is used in our electrical domain, for example. And the next one is that we need some kind of let me say, reliant communication protocol and infrastructure. That can be fiber optics, that can be also 4G and LTE modems. So we are fine with this also. So all, let me say, secure infrastructure where we can get the data transported can be used for this application. So we don't have some limitations that we need to have it, for example, in a very, very fast way, like goose messages or whatever. That is not the case in this way. So we have some kind of check the data up front before we do the self-healing, and that we can use any protocol.
Thank you. That was quite a comprehensive answer. We'll take that as the last answer right now, right here on stage. So thanks for the questions you put in the chat. Thanks, Oliver, for all the answers. And if questions come to your mind later, you have the option. Go to the exhibition area and try and find the expert. I don't know how long will you be there, Oliver, for chatting?
At least until, let me say, the next 6 hours.
Okay, thanks. Though that sounds great, Oliver will be there today to answer your questions there live. And if questions come to your mind later, or maybe during the night you don't want to be called there, give him a texting, give him a chance to answer you, for example, via LinkedIn, or contact your local dealer. So somehow we'll get back to you and you will get back to us. We already mentioned the recording. It will be automatically available to you. And now I'm looking forward to see you in one of the next sessions. We still have an interesting day in front of us. Oliver is probably looking forward to meet you in the expert room. I'm looking forward to keep you here in the line in the studio room, because in about 15 minutes, my next speaker here on stage will be Yelica Rojas, and she will talk about effective asset and lifecycle management with our universal protection relay. So thanks for your questions. Thanks for your time and staying with us. Thank you, Oliver, for the presentation and for the answers. See you in the exhibition area and see you in one of the next presentations. Goodbye for now.
Goodbye.